In this video, we're going to look at correlation and in particular the product moment correlation coefficient. Initially, we're going to look at this topic in a very formulaic way. In the past, you've seen scatter diagrams or scatter graphs. These show two sets of data, which we call bivariate data, and we've seen that we've either got a positive correlation, a negative correlation, or no correlation, or at least no linear correlation. So an example that you might have met before, if you have a positive correlation, that might be now the temperature and the sale of ice creams. So as the temperature goes up, the sale of ice creams goes up. As one goes up, the other goes up. An example of negative correlation might be now the temperature and hot chocolate sales. So as the temperature decreases, hot chocolate sales increase. You might have also seen no linear correlation. So typical examples used in textbooks might be hair colour and the football team that you support. So in this video, we're going to extend that and look at to what extent now, how strong is the correlation between two sets of data. And as stated, we use the term bivariate data. So let's go ahead and look at some particular graphs. So what we've got then is the following. We might have this, we might have another, let's put a few of these on here, and we might draw now some sets of data. So we might have something that looks like this. So let's plot some points, let's just put some over here. Now as we can see, this is going to give us a positive correlation. As this value is increasing, this one is. The other scenario is that we have now going the other way where we have negative correlation. So it looks something like that. And then when we have these evenly distributed all over, we can say that this gives us no correlation. Essentially, this is no linear correlation. There might be some other relationship going on, but we can't put these in a straight line. What we're going to look at is the product moment correlation coefficient, and this is given as R, and it simply tells us how well these particular relationships fit to a straight line. So you might have heard in the past the terms strong positive correlation or weak negative correlation. Essentially R, which is the product moment correlation coefficient, tells us now what kind of relationship we have between two sets of data. The value of R goes from negative to positive 1. If it's negative 1, we have perfect negative correlation. If it's positive 1, we have perfect positive correlation. If it's 0, we have no linear correlation. And everything in between gives us some form of positive weak, positive strong, and so on and so forth. Generally speaking now, if we have the modulus of R between 0 and 1, it seemed to be no real linear correlation. So, for example, if you had a product moment correlation coefficient of negative 0.06, that would suggest that there's no real linear correlation. If we have between 0.1 and 0.3, we can say that there's a small correlation. So, for example, if my product moment correlation coefficient was 0.25, we could say that that was now a small positive linear correlation. If it's between 0.3 and 0.5, we can say it's medium. So for example, if we had minus now 0.46, it would be medium in terms of the negative correlation. If the modulus is anything between 0.5 and 1, we generally say it's strong. So if I had 0.89, we would say it's strong positive correlation. Now, those values are open to a bit of interpretation, but generally speaking, those are some figures banded around when we're looking at this topic. Okay, so let's go ahead and look now at this value of R. So the product moment correlation coefficient. We've got now R is equal to SXY divided now by the square root of SXX multiplied now by SYY. In another video, I'm going to look at this in more depth. Often in the modules that you study, this is seen as simply plugging the numbers in and getting some idea now of the correlation and interpreting it in a given situation. Let's first look at these values right here. Let's take SXX. SXX is the sum of x squared minus the sum of x all squared over n. Now you could write this if you liked as, and it's slightly hard to work with, now the sum of, we've got xi minus x bar, and when we take this squared. This is easier to work with, and in many formula books you'll be given this. If you want to look at this now as the variance multiplied by n, that's essentially what it is. SYY is going to be exactly the same, just with y. So we got the sum of y squared minus the sum of y squared over n. And then finally we have this value right here. Now this determines what whether we have a positive or negative value. This simply now regulates r to ensure that it's between negative and positive 1. It's this top bit that's quite important. Now Sxy is given to be, now we're going to have the sum of x, so we have the sum of x multiplied by y minus the sum of x now multiplied by the sum of y over n. So this is Sxy, and it's this quantity right here. Okay, so how do we go about working these out? Well, essentially we're going to be given a table of values and we're going to plug the data in. If you wanted to look at this is often easier to see that this now is the sum of x. We'd have xi minus x bar, and then we're going to multiply that by y minus, so y1 minus y bar. And if we've got now a negative value when we do this, quite clearly we're going to have now a negative value of r, because that's in the numerator. If this is positive, then we're going to have positive. And as stated in a later video, we will look at how that works. So let's put this in action with some values. So what we're going to do here is just make up some data as we go. So let's now have two sets of data. Let's say we've got maths scores and physics scores. So what we'll say then is maths, let's take maths to be the x. So let's have x, which is going to be maths, and y, which is going to be physics. So these are some scores. So x is maths, and then we're going to have now y is physics. Now I'm going to do this actually from the table. Often in early examples, you're given what they call the summary statistics. So you might be given now SXX or SXY to make your life slightly easier. So let's go ahead and do this. So what we're going to have, let's say we've got now someone scores 1 in the maths test and they score 2 in the physics test. Let's say someone scores 2 in the maths test and 4 in the physics test. As you can see at the moment, we've got correlation. 1, 2, 2, 4. Now what I'm going to do is just make one slight change. Let's say someone got 5 and we expect them to get 10, but let's say they got 9, okay? Let's say someone got 3 and 6, and let's say we got 6 and 12. So in theory, our value of r should be very close to 1. This is almost perfect positive correlation. So we can see now that we've got these values. This value of r is telling us how closely now it fits a straight line. So let's go ahead and let's say now r is going to be sxy over the square root now of sxx multiplied by syy. So let's calculate each of these. Now this is quite taxing, and I strongly suggest that you store the values on the calculator as you go. So let's go ahead and first work out sxx. So this is going to be the sum of x squared minus the sum of x squared over n. Okay, so let's get some x squared terms. So if I just put x squared above, that'll be 1, 4, 25. Then we're going to have now 9, and we're going to have 36. So let's go ahead and work that out. So what I need to do is sum all of these. So in a calculator, let's sum those up. So we've got 1 plus 4 plus 25 plus 9 plus 36. And that gives me now 75. So that's quite a nice number to work with. I don't have to worry. Often these give us quite horrendous values and we need to store them in the calculator. Later on I'll show you how to do that. Okay, let's go ahead now, and what we're going to do is now subtract away the sum of x squared over n. So what we'll do, we'll square this, so let's go ahead and square that. So we've got 1 plus 2 plus 5 plus 3 plus 6. That gives me now 17. So I'm going to square that, and that will give me 289, and then I'm going to divide it by the number of terms. So dividing that by, how many have we got? We've got 5, haven't we? So that's going to give me 289 over 5. So minus 289 over 5. So let's see what that's going to give me then. What do we have? We can say therefore SXX is going to be equal to, and I will store this in the calculator, 75 minus my answer. So that's going to give me 86 over 5. So that's going to be 86 over 5, and we'll store this in as A. I like to write it if I'm doing this formally in pencil now, so shift store A. Again, it's an easy enough value to write in the calculator. Okay, let's now look at SYY. This is going to be the sum of y squared minus now the sum of y all squared over n. So let's go ahead and do that. So first what we need here is going to be y squared. So that's going to give me 4, 16, 81. We're going to have 36 and we're going to have 144. So let's go ahead and add all of those up. And again, just do this straight through a calculator. Don't worry about doing it manually, as you may make errors. Okay, well, I may make errors, I should say. So what's that going to give me? That's going to give me 281. So we've got 281 minus now, we need to sum all of these, square them and divide them by the number. So we'll have 2 plus 4 plus 9 plus 6 plus 12. That gives me now 33. I'm going to square that. That gives me 10,089, and then I'm going to divide that by 5. So we end up now with 10,089 over 5. So let's write that in, 10,089 over 5. So what's that going to give me? That's going to give me SYY, and SYY is going to be 281 minus this value. So 281 minus my answer, and that gives me 316 over 5. So 316 over 5, and I'm going to store that in as B. Again, you can see that that's not not a problem putting that back in the calculator, but I like to get into the habit of now writing A and B to ensure the level of accuracy. Okay, let's now look at SXY. So what we've got then is the sum of x multiplied by y minus the sum of x multiplied by the sum of y over n. Now at this stage it would have been better if I hadn't have squared these, because remember I've already worked out the sum of x and the sum, let's put x, y, sum of x is sum of y over n. And that's, I've already squared this, so perhaps, writing it out to begin with would have been better. So let's see what we're going to get. I'm now going to multiply the sum of these multiplied. So multiplying these, we're going to have 2 plus 8 plus 45 plus 18 plus now the 72. So all I've done is now summed the product xy. So I'm just summing these right here, and that's going to give me now 148. So let's just check I've got all of those right. So I've got 2, I've got 4, 45, 18. That last one should be 72, shouldn't it? 6 times 12 is going to give me 72. So let's do that. So that gives me now 145. So let's write 145 down. Okay, now we're going to subtract away these two. Now the sum of x multiplied by the sum of y. And again, if I'd been more careful, I could have just done this. So what we're going to have then is 1 plus 2 plus 5. This is now the sum of x plus 3 plus 6. And we'll now multiply this by the 2 plus the 4 plus the 9 plus the 6 plus the 12. And on that we're going to have now 561. So 561 divided by the 5, and that's going to give me this value right here, 561 over 5. Okay, so let's go ahead and do that. So 561 over 5. Therefore, what we can say then is SXY is going to be 145 minus this value. So let's do that, 145 minus my answer, and that's 164 over 5. So 164 over 5, and we'll store this in as C. Again, don't need to for this particular case, but it's just getting you into those habits. Okay, let's just think about what we've got here. Now, if we look at this as a graph and we plotted this as a scatter graph, we've got near positive, now perfect positive correlation. So we've got 1, 2, let's do this, 1, 2, we've got 2, 4, we've got 5, 9, which is just slightly off. Then we've got now the 3, 6, and we've got 6, 12. It's going to look something like that. So this idea of R is just how well it fits this straight line. If it's bang on, it's going to be 1, and this isn't too far off. Again, that's done by hand. So what we're going to do is work out this right here. So we've got now R will be equal to, so we've got 164. So we've got the 164 over 5 divided now by the square root of these two multiplied. So we're expecting a value very, very close to 1. So 86 over 5. And we're going to multiply that now by, what's that, 316 over 5. And again, you can see that simplifies slightly, but I'm going to now just put in the calculator that this is going to be C divided now by the square root of A times by B. I know those values are in there, and that's going to give me now 0.9948 and so on and so forth. So let's write that there, 0.994 ... What have we got? 835. So I'm going to give this now to 4 significant figures, 0.9948. So we can see that's pretty good. That's pretty close to 1. And again, different scenarios will yield different things. If we've got very little correlation, then again, this is going to be close to 0, either side of 0, minus 0 point something or other. So this is very, very strong. So that's an example, and I kind of looked at these numbers and thought, well, I'll just make them, we know they're generally going to fit to that straight line, therefore it should be close to 1. Okay, let's have a go at another one. Let's do a different one. Let's put up a different table. Let's now look at the number of waiters on shift in a fast food restaurant, the time taken to get the food to the table. So let's say waiters, okay, let's say waiters and time. Now we've been dealing with X and Y. It won't always be the case that you have X and Y. We might have W and T. And in this case, I'm going to use this. You might have S and T. You might have other variables. So let's just plug some numbers in. Let's say there are 10 waiters on and it takes 6 minutes now to get the food to a table. Let's say we got 4 on and it takes 9. Let's say we got 12. Let's just make some numbers up. 12 and 3. Let's go 5 and 8. Let's go now 11 and 2. So if we wanted to look at this now, we could plot this, and what we'd have now is something that looks like the following. As the number of waiters increases, generally speaking, the time taken for food to arrive is going to decrease. So there's time and there's waiters. So if we plotted the first one, let's say it's going to be about there, 10:6. Let's look at the next one. The next one's going to be about 4:9, which is going to be there. Then we've got 12 and we've got 3, which will be about there. We've got 5 and 8. Which, give or take, let's have a look at this. 5 and 8 is going to be, let's say, it's about there. And then 11 and 2, let's say 11 and 2 is going to be about there. Okay, so really quite, very rough. But we can see that there's some negative linear correlation going on here. So when we work out the product moment correlation coefficient, we should have a number that's negative and not a million miles off being 1. So let's have a look at this. Let's go ahead and do this. So what we're going to say then is R is going to be now, and we can say that this is going to be SWT over now, and we're simply going to have the square root of SWW multiplied by STT. So don't worry about now that these not being X and Y. If you really must, you can go ahead and just change them over. But you must, of course, in an exam, put your answer back in terms of W and T. Okay, let's first look at SWW. So what we've got is SWW. So that's giving us the sum of W squared minus now the sum of W all squared over N. So when you met variance before, this is simply N multiplied by the variance. If you like, you can see it that way, you don't have to. So what we're going to have then is the following. If we consider now we've got W squared, that's going to be 100, that's going to be 16,144. Then we're going to have now 25 and 121. So let's go ahead and add that up. So what we've got then is 100 plus now 16 plus the 144 plus now the 25 plus the 121. So do check when you're plugging these in just to ensure that you are remaining accurate. So that's going to be 406. Now we're going to subtract away. So this time, let's just sum this. And I'm going to actually sum it because I'm going to use this later. 10 plus 4 plus 12 plus now the 5, so plus 5 plus 11. So that's going to give me 42. So what I'm just going to do is put here now 42 squared. So 42 squared, and again, I'm just using 5 bits of data, just to make my life slightly easier. So let's square that, and that will give me that, divide that by 5, and then all we're going to do is do 406 minus my answer. So that gives me now 266 over 5, so let's write that in. Therefore, we can say now that SWW is going to be 266 over 5, and I'll store that in as A. Again, nice enough number to deal with, it's nothing too hideous, so let's go ahead and store that in as A. Okay, let's look at the sum of TT, or STT. So we've got the sum of T squared minus now the sum of T all squared over N. So let's go ahead and now look at T squared. So let's write T squared below. There's T squared, 36, 81, 9, 64 and 4. So let's go ahead and sum those. So we've got 36 plus now 81 plus 9 plus 64 plus now 4. And that gives us 194. So let's just check that. Got all of those incorrect. 194. As you can see, making an error is going to be catastrophic, especially when you're working to high levels of accuracy. Okay, let's sum these up now. Let's sum T. So we're going to sum T. So 6 plus 9 plus 3 plus 8 plus 2. Perhaps a bit lazy of me. So that's going to be 28. So we got 28 squared over 5. So let's go ahead and work out STT. So STT. So let's do that then. So if we square this, and then we're going to divide that by 5, and then we'll do 194 minus that answer, and that'll give me STT. So what have we got? We've got 186 over 5. So let's store that in as B. Shift store B. Okay, so that's going to give us that 186 over 5. So 186 over 5, and that's B. Right, okay, let's now look at the next one. So what we've got then is SWT. Okay, so we've got now the sum of WT minus the sum of W multiplied now by the sum of T now over N. So what have we got? If we multiply these, let's go ahead and multiply these, we're going to have 60 plus now 36 plus 36 plus 40, and then we're going to have plus 22. So let's check I've got all of that in. What's that going to be? 194. So that's 194. Now, if I look at these two values, this is going to give me the sum of W and now the sum of T. And that's where I should have, in the last one, just been a bit more switched on and just done that. So that's what we get. Okay, so let's go ahead and work that out. So let's grab that up. So let's now subtract away from that. What we'll have is the following. We've got now 42 times by 28. And if we divide that now by the 5, that's going to give me now on here minus 206 over 5. Now this goes back to my point earlier. Let's just put this in. Let's put this in. So we got now SWT minus 206 over 5. And let's just store this in as C. So let's go ahead and store that. So shift store C. Okay. So if we look at these now, we've got A is in as the 266 over 5. B is in as the 186 over 5, and C is now the negative 206 over 5. As stated, those values are fairly straightforward to work with. So what you can see now is that essentially now the product moment correlation coefficient R is governed by this product here. And in a later video, I'll look at exactly why that is. Essentially, it's all about the placing now on the coordinate axis of the two values in relative now to what we call x bar and y bar, the mean of y and the mean of x, or in this case the mean of w and the mean of t. So if we just look at that now, let's just draw a quick, before we work this out, just to give some idea of what's going on. So what we might have is the following. Let's put this up. We might now decide that we're going to put now this value right here, and this is going to be x bar, y bar. So if we think about this, this is x bar and this is going to be y bar. So here what we've got now is x minus x bar, comma, y minus y bar. So if we think about this now, if we multiply these two, both of these are going to be positive values. If we just think, if this is going to be the mean just here, this now is x bar, y bar. These are both going to be positive. Now, if they're in here, x bar is going to be negative, y bar is going to be positive. If they're both in here, what we're going to have is negative and negative. And of course, negative times by negative is positive. Here, we're going to have positive x bar, negative y bar. So you can see now that when we end up summing all of these, if we have now a negative correlation, and remember, negative correlation, essentially we're going to have the vast majority of these observed values in this quadrant right here and this one. That's why we get the negative. Yet if we have most in these two quadrants, the first and the third, most of them are going to be positive. And this governs now what we get in terms of the numerator, and that's how we essentially find out. In a later video, I'll look at this in more depth, but this is essentially how it works. It's just now the product of these two, and when we sum it now, all of those, when we sum them up, we get either a positive value or a negative value. If we get something close to zero, it's simply telling me that these are scattered or generally fairly evenly distributed across the four quadrants, and that's why the sum ends up being close to zero, because you've got a lot of positives and you've got a lot of negatives, and then essentially they cancel each other out. More of that in another tutorial, but hopefully that's just given you a bit of an insight of why this works. So if we just look at this, we can see now that if we got now negative correlation, we got lots of these negative values just here. Okay, so let's go ahead and do this. So let's go ahead, and what we'll have is the following. So we can say now that R, which is a product moment correlation coefficient, is going to be now minus 206 over 5, now over the square root of 266 over 5 multiplied by the 186 over 5. So let's now write that out, and remember all of these are stored in the calculator. So in this case we're looking at now, it'll probably be about 0.9, somewhere around there. It's pretty good. It's pretty good. You know, you can see that there is some linear relationship between these two quantities. So let's go ahead and do that. Let's work this out. So in the calculator now, I'm just going to push here. So we're going to have recourse C over now the square root of A multiplied by B. If you're unsure, just put the numbers in. And that gives us now negative, what have we got? Negative 0.926. And that's what we were expecting. We're expecting, let's put that in, 0.926. And let's go on with that, 1, 2. So 1, 2, 5, dot, 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 and so on and so forth. So if you wanted to round this now, let's round this. Let's go for 4 significant figures, 9261. So let's put 4SF. So as you can see, that's pretty, we kind of knew that was coming anyway. These are getting very close to being on this straight line. And that's what R is all about. It's just simply saying, how close do these fit to a straight line? So if you wanted to sketch these up, let's just have a look at, let's take a really, really rough idea of what we would envisage happening. So let's look at a few different examples. And as stated, these are going to be very, very rough, but it just gives you some idea. So let's have a scenario where we have, and I'll just write them out here. If we have now R is equal to 1, let's say now that R is equal to minus 1, let's say R is equal to 0.1, we might have, for example, R is equal to minus 1/2. We might have R is equal to, let's say, positive 1/4, and let's say that R is equal to negative 0.02. Okay, as you can imagine, these are going to fit plumb along a straight line. So this is perfect positive correlation. So we'll get all of our values sitting just like so, okay? Now, if it's minus 1, we're going to get now the opposite. We're going to have a straight line, and these are going to now all fit bang on. So what we've got then is the following, and look, something like this. Okay, with R being 0.1, then it's a very, very faint relationship, but not an awful lot. You might end up with something that looks like this, okay? It might do something. That's not brilliant, but it might be a slight, but very, very little at most. If we have now R is equal to minus 1/2, what we've got then is some negative correlation. Now, in terms of what you might want to call a line of best fit, if we look at that, you might have things that are roughly dotted around, okay? And these are just sketches, okay? Don't read too much into them. So it might look something like that. So they're not bang on a line, but you can see the general flow of these. So you might get some out here, and it'll look something like that. If we got r is equal to a quarter, then we've got fairly weak positive correlation. So again, if we had now a line of best fit, we'd have something that meandered, I think that's a good word, it meandered towards this. So this is not brilliant, but it gives us some idea that there is some slight positive correlation going on. And again, this one is going to be very, very much a case. Now you could look and analyse which of the quadrants these are in relation to x bar and y bar, but essentially you're going to see very, very little now linear correlation. Now this, again, take these for what they are. They're by no means the most accurate things in the world. But we do have to be careful now with the product moment correlation coefficient, because this is telling us about now the linear correlation between the two. So for example, now if I drew up something that looked like this, and I went ahead and let's just put on a circle, or let's put on an ellipse. Now I might have some observed values, and these observed values might be sitting in some formation like this, and they might be bang on some other non-linear relationship between the two. So if we calculated the product moment correlation coefficient for these, it would tell us now that this would potentially be very close to 0. The thing is though, we have to look at other relationships that are going on. So there are limitations with the product moment correlation coefficient. We also have to consider when we have a product moment correlation coefficient that is looking like it's strong positive or strong negative correlation, but essentially there's no direct relationship between the two sets of data. If you like, you could say correlation doesn't necessarily mean causation. So if you've ever heard the terms now, the explanatory and response variables, so for example, as time changes, height changes, it's not always the case. We might have, for example, we could say along the lines of, let's just go for anything that's not related. Let's say now, by fluke, we had children's hair colour and the number of ice creams they bought, and it gave us now the product moment correlation coefficient of 0.89. You would think that there's some relationship, but they're not necessarily linked. So do be aware that this has its limitations. So in a later video we will look more in depth, but essentially now the take-home message is as follows. If you want the product moment correlation coefficient, R is equal to SXY over now the square root of SXX multiplied by SYY, and this will give you now a value between negative and positive 1. If it's negative 1, you've got perfect negative correlation. If it's positive 1, perfect now positive linear correlation. Anything in between now will either be weak or no linear correlation. So there we go. Hopefully that's now been a good brief introduction to the topic for you.